Right now, as you listen to this, something is happening that cannot be undone. Not because of some mysterious force, not because the universe is breaking, but because of a single quantity buried deep in the laws of physics, one that quietly dictates the direction of almost everything that happens, everywhere, at every scale. It governs why ice melts in warm water, but warm water never spontaneously freezes around an ice cube. It explains why you age, why stars burn out, and why a shattered glass will never leap off the floor and reassemble itself. Scientists call it entropy. Most people think it just means disorder or chaos. It doesn't. What entropy actually measures is far stranger and far more powerful than that. And once you understand what it really is, you will never look at a cooling cup of coffee, a rusting bridge, or even the flow of time itself the same way again. Before we go any further, if you find these kinds of deep explorations fascinating, a quick like or subscribe genuinely helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with the way most people first hear about entropy, because it's almost always wrong, or at the very least, dangerously incomplete. You've probably encountered it in a science class or a popular article. Someone holds up a messy bedroom and says, "See? Entropy. Things naturally go from order to disorder. A tidy desk becomes cluttered, a sandcastle crumbles, an egg falls off a counter and shatters across the kitchen floor." The story sounds intuitive. Things fall apart. Messes are easier to make than to clean. Entropy, you're told, is just nature's preference for chaos. And because it matches your daily experience, you accept it. Tidying up is hard. Making a mess is easy. Entropy increases. Case closed. But here's the problem. That explanation isn't really what entropy is. It's a loose analogy wearing a lab coat, and it leads people into all sorts of confusion. Because if entropy were truly just about messiness, then cleaning your room would violate a law of physics. Running a dishwasher would be illegal according to the universe. Clearly, something deeper is going on. The real definition of entropy has almost nothing to do with how tidy or messy something looks to human eyes. A room with clothes scattered on the floor isn't in a high entropy state in any physically meaningful sense. A gas spread uniformly through a container looks featureless and bland. Yet that uniform state has enormously higher entropy than a gas with visible swirls and patterns, which looks far more complex to the eye. Order and disorder, as we casually use those words, are human judgments. They depend on what we consider neat or messy. Physics doesn't care about neatness. Physics cares about something far more precise. And understanding that precise thing is the key to understanding why entropy governs so much of reality. So, let's throw away the messy room. Let's forget about disorder for a moment, and let's talk about what entropy actually measures. At its heart, entropy is a count. Not a count of objects or particles, but a count of possibilities. Specifically, entropy measures how many different microscopic arrangements of a system are compatible with the large-scale condition you observe. Everything else about entropy, the second law, the arrow of time, heat-death, all of it flows from that single idea. The words sound abstract, so let's make them concrete. Imagine you have 10 coins. You lay them all out on a table. You can see each coin. Each one is either heads or tails. Now, suppose someone walks into the room and you tell them, all 10 coins are showing heads. How many different ways could the coins be arranged to match that description? Exactly one. Every single coin must be heads. There is only one microscopic arrangement, one specific configuration of individual coins that produces the large-scale outcome of all heads. Now suppose instead you tell them 5 coins are heads and 5 are tails. How many ways could the coins be arranged to match that description? This time, there are many ways. You could have the first 5 coins as heads and the last 5 as tails. Or you could alternate heads and tails. Or you could have heads scattered randomly among the 10 positions. If you work out the mathematics, there are exactly 252 different ways to arrange 10 coins so that exactly 5 show heads and 5 show tails. 252 arrangements all look the same from the outside. They all satisfy the same large-scale description, 5 heads and 5 tails. But the specific coins showing heads are different in each case. This is the core idea. The state, all 10 heads, has only one arrangement behind it. The state, 5 heads and 5 tails, has 252. In the language of physics, each specific coin configuration is called a microstate. The large-scale description you observe is called a macrostate. Entropy measures how many microstates correspond to a given macrostate. More microstates means higher entropy. Fewer means lower. All heads with only one microstate has very low entropy. 5 and 5 with 252 has much higher entropy. That is what entropy fundamentally is, a measure of how many hidden microscopic arrangements are consistent with what you see at the large scale. It doesn't care whether the arrangement looks neat or messy to your eyes. It cares about how many different ways the underlying pieces could be organized while still producing the same overall appearance. Now, 10 coins is a toy example. The numbers are small and manageable. But the physical world doesn't deal in tens. It deals in numbers so large they break your intuition. A single glass of water contains roughly 10 to the 24th molecules. That's a 1 followed by 24 zeros. About a trillion molecules in something you can hold in one hand. Each of those molecules has a position. Each one has a velocity. Each one is vibrating, rotating, bouncing off its neighbors millions of times per second. The number of possible microscopic arrangements of all those molecules is not just large, it's a number so staggeringly vast that writing it down would take more paper than exists on Earth, more digits than there are atoms in the observable universe. When you look at a glass of water sitting on a table, it looks calm and uniform. The water is the same temperature throughout. The surface is still. Nothing dramatic is happening. But underneath that calm surface, there are an almost incomprehensible number of different ways the individual molecules could be arranged, while still producing that same calm, uniform glass of water. Each arrangement is a different microstate, and the number of those microstates is what entropy counts. This is why entropy is so powerful. Not because it's a mystical force that drives things toward chaos, but because the mathematics of large numbers is overwhelmingly one-sided. When you have a trillion particles, the number of arrangements that look uniform and spread out is so astronomically larger than the number of arrangements that look concentrated or special, that the probability of ever stumbling into a special arrangement by chance is effectively zero. Not small, not unlikely, effectively zero. Think about it this way. Imagine all the air in the room you're sitting in right now. Oxygen and nitrogen molecules are bouncing around at hundreds of meters per second, colliding with each other billions of times per second. Every collision sends molecules flying in new directions. The molecules are constantly rearranging themselves. At any given moment, the air could, in principle, be arranged so that every single molecule happened to be in the left half of the room, leaving the right half a perfect vacuum. There's no law of physics that prevents this. Every molecule is free to be wherever it wants. The arrangement with all molecules on the left is a perfectly valid microstate, but the number of microstates where the molecules are roughly evenly distributed throughout the room is so overwhelmingly, incomprehensibly larger than the number of microstates where they're all crammed into one half, that you could wait for the entire age of the universe, trillions upon trillions of years, and it would never happen. The odds aren't just small, they're so small that calling them small is an insult to the word. Let's put numbers on this. Suppose your room has just 1,000 molecules of air. That's absurdly few. A real room has something like 10 to the 26th molecules. But even with just 1,000, the probability that all of them happen to be in the left half at the same moment is roughly 1 in 2 to the 1,000th power. 2 to the 1,000th is a number with about 300 digits. The odds are 1 in that number. For perspective, the number of atoms in the entire observable universe is about 10 to the 80th, a number with 80 digits. The probability of even 1,000 molecules spontaneously clustering is vanishingly smaller than anything that could ever happen in the entire observable universe. And remember, a real room has not 1,000, but something like 100 trillion molecules. At that scale, the probability becomes so ludicrously small that mathematicians essentially treat it as zero. This is the tyranny of large numbers. When you have enormous numbers of particles, statistics doesn't just suggest what will happen. It dictates what will happen, with a certainty so absolute that it might as well be a law. And this is exactly why entropy always increases. Not because there's a rule forcing it, but because there are so overwhelmingly many more high entropy arrangements than low entropy ones, that any random change to the system almost certainly moves it toward higher entropy. The system isn't being pushed, it's wandering randomly. But the landscape of possibilities is so absurdly tilted that random wandering always ends up in the same place. The physicist who made this connection, who took entropy from a vague thermodynamic bookkeeping tool to a deep statement about the structure of physical reality, was Ludwig Boltzmann. Working in the late 1800s, Boltzmann was one of the most brilliant and tragically underappreciated scientists who ever lived. At a time when many physicists didn't even believe atoms existed, Boltzmann built an entire framework showing that the behavior of heat, temperature, pressure, and entropy could all be explained as the statistical behavior of enormous numbers of tiny particles bouncing around and colliding. His insight was radical. The properties we observe at the large scale, the temperature of a gas, the pressure in a container, the way heat flows, these aren't fundamental. They're averages. They emerge from the collective behavior of countless individual atoms and molecules. Temperature, for instance, isn't a thing that exists at the microscopic level. A single molecule doesn't have a temperature. Temperature is the average kinetic energy of an enormous number of molecules. It's a statistical property, meaningful only when you have enough particles for averaging to make sense. And entropy, Boltzmann realized, works the same way. It's not a mysterious essence or a cosmic tendency. It's a count of microscopic possibilities. And he captured this insight in what might be the most important equation in all of physics. It's carved on his tombstone in Vienna. S equals K log W. S is entropy. W is the number of microstates, the total number of microscopic arrangements compatible with the macroscopic state you observe. The log is a logarithm, which essentially converts the incomprehensibly large numbers involved into something more manageable. And K is a constant, now called Boltzmann's constant, a tiny number that bridges the microscopic world of atoms to the macroscopic world of thermometers and steam engines. The equation says something beautifully simple. The entropy of a system is proportional to the logarithm of the number of ways its microscopic components could be arranged while still looking the same from the outside. More arrangements, higher entropy. Fewer arrangements, lower entropy. That's it. The equation fits on a single line. It contains no complicated mathematics, but its implications are enormous. It tells you that entropy isn't about disorder in any colloquial sense. It's about multiplicity. It's about how many hidden configurations exist behind what you observe. And it tells you that the second law of thermodynamics, the law that says entropy tends to increase, isn't really a law in the same way that Newton's laws or Maxwell's equations are laws. It's not a fundamental rule imposed on the universe from outside. It's a statistical inevitability. When you have enormous numbers of particles, the system will almost certainly evolve toward the macrostate with the most microstates, simply because that macrostate is overwhelmingly more probable than any other. Saying entropy increases is like saying that if you shuffle a deck of cards enough times, you'll almost certainly end up with a random-looking arrangement rather than a perfectly sorted one. Not because shuffling has a preference for randomness, but because there are so astronomically more random arrangements than sorted ones that hitting a sorted arrangement by chance is practically impossible. Let's extend this analogy because it reveals something important. Take a standard deck of 52 cards. The total number of possible arrangements of that deck is 52 factorial. That's 52 times 51 times 50 times 49, all the way down to 1. The result is a number with 68 digits, about 8 times 10 to the 67th. Now, out of all those possible arrangements, how many are perfectly sorted? Depending on how you define sorted, there are maybe 24. Sorted by suit and rank in ascending order, sorted in descending order, a handful of variations. Let's be generous and say there are 100 arrangements you'd recognize as neatly sorted. That means the fraction of sorted arrangements is roughly 100 divided by 8 times 10 to the 67th. That fraction is so small, it's effectively 0. If you shuffled a deck once per second for the entire age of the universe, roughly 4 times 10 to the 17th seconds, you'd have explored an absurdly tiny fraction of all possible arrangements. The probability of randomly landing on a sorted deck is so low that it has never happened in all of human history, and almost certainly never will. And a deck of cards has only 52 components. Physical systems have trillions of trillions. The numbers become not just large, but incomprehensibly, cosmically large. A glass of water at room temperature has an entropy corresponding to a number of microstates that would require a number with roughly 10 to the 23rd digits just to write down. Not the number itself, the number of digits in the number. Your brain cannot process this. No human brain can. These numbers are so far beyond anything we encounter in daily life that they exist in a realm of mathematics that has no analogue in human experience. And this is precisely why entropy is so reliable. When the number of high entropy microstates outnumbers the number of low entropy microstates by factors this extreme, the system doesn't occasionally visit low entropy states. It never visits them. Not in practice. Not in principle for any practical timescale. Not if you waited until every star in the universe burned out and every black hole evaporated. The mathematics is simply too overwhelming. This is why entropy is different from other physical quantities. Energy is conserved. Momentum is conserved. These are symmetries of the laws of physics, elegant and exact. But the second law, the increase of entropy, isn't a symmetry. It's a consequence of counting. It emerges because physical systems have so many components that the statistics become essentially deterministic. Boltzmann understood this. He knew the second law was statistical, not absolute. In principle, entropy could decrease. All the air in your room could rush to one side. All the heat in a cold cup of coffee could spontaneously concentrate back into a hot spot. These events are allowed by the laws of physics. They're just so improbable that they will never actually happen in any realistic scenario. When people say entropy always increases, what they really mean is that the probability of it decreasing is so vanishingly small that no exception has ever been observed in the history of science, and none ever will be under normal circumstances. The law is statistical, not absolute, but the statistics are so extreme that the distinction is academic. There's something else crucial to understand about microstates and macrostates, and it addresses a common confusion. Some people hear the microstate explanation and think entropy is subjective. After all, the macrostate depends on what you choose to measure. You could describe a gas by its temperature and pressure, or you could track every molecule individually. Different descriptions give different macrostates and different entropy values. Does this mean entropy is just in the eye of the beholder? No, and here's why. While the exact numerical value of entropy does depend on your level of description, the direction in which entropy changes does not. No matter how you choose to describe a system, no matter what macroscopic quantities you track, the number of microstates compatible with the system's future states is overwhelmingly larger than the number compatible with its past states. The increase in entropy is robust. It doesn't depend on your choice of variables. It doesn't depend on how much you know. The asymmetry between past and future states is built into the mathematics of large numbers, not into the observer's perspective. The coarse graining, the level of description you choose, affects the specific entropy number. But the relentless statistical drift toward higher entropy happens regardless. It's as objective as gravity. There's also a subtle but important point about what entropy is not. Entropy is not energy. It's not a force. It doesn't push things around. It doesn't exert pressure or create motion. Entropy is a property of a system's state, a way of characterizing how many microscopic configurations are available. When a hot object cools down, entropy increases. But it's not entropy that's doing the cooling. The molecules in the hot object are simply colliding with the molecules in the cooler surroundings, sharing kinetic energy through random impacts. The cooling happens because of forces between molecules, electromagnetic interactions at the atomic level. Entropy is the bookkeeping. It's the ledger that tracks how many arrangements are available before and after the energy has spread around. And that ledger overwhelmingly favors the spread-out state. This distinction matters because it prevents a mistake that even some textbooks make. Entropy doesn't cause things to happen. Entropy describes what happens when fundamental forces act on enormous numbers of particles. If you remove the particles, or remove the forces, entropy doesn't do anything on its own. It's not an agent. It's not a driver. It's the deepest accounting system in physics, keeping track of probabilities so extreme that they govern the direction of everything from chemical reactions to the evolution of the cosmos. So where does this leave us? We've replaced the vague idea of disorder with something far more precise and far more powerful. Entropy counts microstates. It measures how many hidden microscopic configurations are compatible with the macroscopic state you observe. Systems evolve toward higher entropy not because some force pushes them there, but because higher entropy states are so overwhelmingly more numerous that alternatives are statistically impossible. This isn't a law imposed from outside. It's the natural outcome of having vast numbers of particles governed by simple rules. The universe doesn't prefer chaos. It doesn't prefer disorder. It doesn't prefer anything. It simply has access to an unimaginably vast landscape of possibilities, and almost all of those possibilities look, from our macroscopic perspective, like high entropy. That's the insight Boltzmann carved into the foundation of modern physics. S equals K log W, a count of possibilities. The most democratic equation in science, where every microstate gets an equal vote, and the majority wins by margins so extreme that the outcome is never in doubt. But understanding what entropy measures is only the beginning. Because this counting of microstates, this statistical framework, connects directly to something you experience every day. It connects to heat. It connects to energy. It connects to the reason why your coffee cools, why engines waste fuel, and why you can never, ever get something for nothing. Now that we understand what entropy actually counts, let's talk about how humans first stumbled onto it. Because entropy didn't enter physics through abstract mathematics or philosophical speculation, it entered through something far more practical. Steam engines, factories, the urgent industrial need to turn heat into useful work, and the frustrating, maddening discovery that you can never do it perfectly. No matter how cleverly you design the machine, no matter how precisely you engineer the parts, some energy always slips away. Always. Without exception. That frustration, that inescapable inefficiency, is where entropy first showed its face. And the story of how scientists uncovered it reveals something profound about the nature of energy itself. In the early 1800s, the Industrial Revolution was reshaping Europe. Steam engines were powering factories, trains, and ships. These machines burned fuel, usually coal, to boil water into steam. The steam expanded and pushed pistons, which turned wheels and drove machinery. The hotter you made the steam, and the more pressure you built up, the more work you could extract. But engineers noticed something troubling. No matter how good their engines got, most of the energy in the fuel was wasted. It escaped as heat into the surroundings, into the exhaust, into the cooling water, into the warm metal of the engine itself. Even the best steam engines of the era converted only a small fraction of the fuel's energy into useful mechanical work. The rest was lost, not destroyed, but spread out into the environment in forms that could no longer do anything useful. This wasn't a failure of engineering, it was something deeper, something built into the way heat and energy work at a fundamental level. The first person to truly grasp this was a young French military engineer named Sadi Carnot. In 1824, at just 28 years old, Carnot published a short book with an enormously ambitious goal. He wanted to understand the absolute maximum efficiency any heat engine could achieve. Not a specific engine, not a steam engine or a gunpowder engine, or any particular design. He wanted to know the theoretical limit that no engine, no matter how perfectly built, could ever surpass. Carnot imagined an idealized engine, one with no friction, no heat leaks, no mechanical imperfection whatsoever. And he discovered something remarkable. Even this perfect engine, this idealized machine with no flaws whatsoever, could not convert all its heat into work. There was a fundamental ceiling, and that ceiling depended on only one thing: the temperature difference between the hot source providing energy and the cold sink absorbing waste heat. The bigger the temperature difference, the more efficient the engine could be. But as long as the cold sink had any temperature above absolute zero, the efficiency could never reach 100%. Some heat always had to be dumped into the cold reservoir. Always. This wasn't a limitation of materials or craftsmanship, it was a limitation of nature itself. Carnot didn't fully understand why this limit existed. He was working within an older theory of heat called the caloric theory, which imagined heat as a kind of invisible fluid flowing from hot objects to cold ones. That theory turned out to be wrong. Heat isn't a substance. It's the transfer of energy through microscopic collisions and radiation. But Carnot's conclusion about the efficiency limit was exactly right, and it survived the death of the theory that inspired it. His work sat largely unnoticed for years. He died of cholera at 36, his notebooks unpublished. But decades later, when physicists began assembling the laws of thermodynamics, Carnot's insight became one of the pillars. The person who gave entropy its name and its formal definition was Rudolf Clausius, a German physicist working in the 1850s and 60s. Clausius studied Carnot's work carefully and realized it pointed to something fundamental. He formulated what we now call the second law of thermodynamics, and he stated it in a deceptively simple way. Heat does not spontaneously flow from a colder body to a hotter one. That's it. That single statement, which sounds almost obvious, turns out to be one of the deepest laws in all of physics. Of course, heat flows from hot to cold. You know this from everyday life. A hot cup of coffee sitting on your desk cools down. It doesn't heat up. The warmth leaves the coffee and enters the surrounding air. The ice cube in your drink melts because heat flows from the warmer liquid into the colder ice. You've never seen a cup of coffee spontaneously get hotter while the air around it gets colder. You've never seen an ice cube grow larger while the drink around it warms up. Heat flows one way, hot to cold, always. But why? There's no fundamental force pushing heat in that direction. At the microscopic level, molecules are just bouncing around and colliding. When a fast-moving molecule from the hot coffee hits a slower molecule in the surrounding air, energy transfers from the fast one to the slow one. The fast molecule slows down, the slow molecule speeds up. But the reverse can also happen. A fast air molecule could hit a slower coffee molecule and transfer energy back into the coffee. Individual collisions don't have a preferred direction. They're perfectly reversible. Any single collision could go either way. So why does heat always flow from hot to cold at the macroscopic level, even though individual molecular collisions have no such preference? This is where the microstate counting from earlier becomes essential. When heat flows from a hot object into a cold one, the hot object loses some fast molecules and the cold object gains some. The total energy is unchanged. Energy is conserved. But the number of microstates available to the combined system increases enormously. Here's why. When energy is concentrated in the hot object, with some molecules moving very fast and others moving slowly, the system is in a relatively special arrangement. There are comparatively few ways to distribute the energy so that one object has most of it and the other has very little. But when the energy spreads out more evenly, when both objects approach the same temperature, the number of possible microscopic arrangements skyrockets. There are overwhelmingly more ways for the energy to be distributed roughly equally among all the molecules than for it to be concentrated in a subset. Think back to the coin analogy. Having all the energy in one object is like having all coins showing heads. Having the energy spread evenly is like having roughly half heads and half tails. And we saw that the number of arrangements giving half and half dwarfs the number giving all heads. With a trillion molecules instead of 10 coins, the asymmetry isn't just large, it's so extreme that the concentrated state might as well be impossible. Heat flows from hot to cold because the spread out state has so astronomically more microstates that random molecular collisions will carry the system there with virtual certainty. You're not watching a force push heat around. You're watching probability in action. Probability so overwhelming it looks like certainty. Clausius captured this by introducing a new quantity. He needed a way to track this tendency, this one-way drift of energy from concentrated to dispersed. He called it entropy, from the Greek word for transformation. And he showed that in any real physical process, the total entropy of the universe either stays the same or increases. It never decreases. This is the second law of thermodynamics, expressed in its most general form. The total entropy of an isolated system never decreases. In idealized, perfectly reversible processes, entropy stays exactly the same. In every real process, it increases. No exceptions have ever been observed. Now, let's connect this to energy more carefully because there's a critical distinction that most people miss entirely. Energy is conserved. You learned this in school. Energy cannot be created or destroyed. It can only change form. Kinetic energy becomes thermal energy. Chemical energy becomes light. Gravitational potential energy becomes motion. The total amount of energy in the universe never changes. It's the same today as it was at the beginning. So, if energy is always conserved, if we never lose any, why do we talk about energy crises? Why do we worry about running out of fuel? Why does your phone battery die if energy can't be destroyed? The answer is that energy has quality, not just quantity. Some forms of energy are more useful than others, and entropy is the measure of that quality. When energy is concentrated, when it's in a low entropy form, it can do work. It can push pistons, spin turbines, power muscles. But when the same amount of energy is spread thinly across a vast number of molecules, as diffuse low-grade heat, it's still there, every last unit of it. But it can no longer do anything useful. The energy hasn't been destroyed, it's been degraded. It's gone from a concentrated, useful form to a dispersed, useless form. And this degradation is what entropy tracks. Consider burning a piece of coal. The coal contains chemical energy stored in the bonds between carbon and oxygen atoms. This is concentrated, low-entropy energy. When you burn the coal, that chemical energy converts into heat, into light, into the kinetic energy of hot gases rushing up the chimney. If you use this heat to boil water and drive a steam engine, some of that energy becomes mechanical work, turning wheels and driving generators. But not all of it. Some of the heat escapes into the environment. It warms the air. It heats the ground. It radiates into the sky. This escaped heat isn't gone. It's still energy. But it's now spread across billions of air molecules, each one moving just a tiny bit faster than before. You can't collect that diffuse warmth and funnel it back into useful work. It's been dispersed beyond recovery. The energy is conserved, but its quality has decreased. Its entropy has increased. This is the cruel truth at the heart of thermodynamics. Every time you use energy to do something useful, you degrade some of it into a less useful form. Every engine, every motor, every biological process converts high-quality energy into lower-quality energy. The total amount stays the same, but the fraction that's available for useful work shrinks. This is why your car engine gets hot. The heat pouring off the engine isn't a design flaw you could fix with better engineering. It's the price the universe charges for converting chemical energy into motion. It's entropy increasing. It's energy spreading from concentrated to dispersed. Let's make the efficiency limit vivid. Carnot showed that the maximum possible efficiency of a heat engine is determined by the temperatures of the hot source and the cold sink. If the hot source is at 600 Kelvin and the cold sink is at 300 Kelvin, the maximum possible efficiency is 50%. Half the heat energy can be converted into work. The other half must be dumped into the cold sink. That's not because of friction or poor design. That's the theoretical maximum for a perfect engine. In practice, real engines do worse because they have friction, heat leaks, and other imperfections. A typical car engine converts only about 20 to 25% of the fuel's energy into motion. The rest becomes waste heat. You might ask why. Why can't you just convert all the heat into work? After all, you can convert all work into heat. Rub your hands together. The kinetic energy of your moving hands converts entirely into thermal energy through friction. Every last bit of mechanical energy becomes heat. The conversion from work to heat is complete and easy. But the reverse, converting heat entirely into work, is impossible. This asymmetry is one of the deepest features of the physical universe, and entropy is the reason. Here's why the asymmetry exists. Work is organized energy. When a piston moves, all its molecules are traveling in the same direction. That's a very specific, very low entropy arrangement of molecular motions. Heat, on the other hand, is disorganized energy. Molecules are moving in random directions at random speeds. That's a very high entropy arrangement. Converting work to heat means going from an organized state to a disorganized state, from low entropy to high entropy, from few microstates to many. That's the natural direction. It happens spontaneously. Converting heat to work means going from a disorganized state to an organized state, from high entropy to low entropy, from many microstates to few. That goes against the statistical grain. It doesn't happen spontaneously. You can force it to happen partially, which is what a heat engine does, but you can never do it completely because the statistics forbid it. To convert heat entirely into work, you would need random molecular motions to spontaneously organize into coordinated motion, all pushing in the same direction at the same time. That's like all the air molecules in a room spontaneously rushing to one side. It's possible in principle, but so overwhelmingly improbable that it never happens. This is what makes the second law different from other laws of physics. Newton's laws are deterministic. Apply a force, get an acceleration. Maxwell's equations precisely predict electromagnetic fields. The second law is neither deterministic nor exact. It is a statement about what is overwhelmingly probable when enormous numbers of particles interact. Every other law in physics tells the universe what it must do. The second law merely tells the universe what it will almost certainly do. It is less like a commandment and more like a prediction that has never once been wrong. James Prescott Joule, working in the 1840s, established the equivalence of heat and work. Through careful experiments, he showed that a specific amount of mechanical work always produces the same amount of heat. Energy is conserved across all its forms. This was the first law of thermodynamics, the law of conservation of energy. But Joule's work also made the second law sharper. If energy is always conserved, then the fact that engines waste heat isn't about losing energy, it's about losing the ability to use energy. The first law says you can never win. You can't get energy from nothing. The second law says you can never even break even. You always pay a tax in wasted heat, and that tax is entropy. Let's look at an everyday example in detail. You have a cup of hot coffee at about 70 degrees Celsius, sitting on a desk in a room at about 20 degrees Celsius. You wait. The coffee cools. Heat flows from the hot coffee into the cooler air until both reach the same temperature, somewhere around 21 or 22 degrees. Energy has been conserved. The heat that left the coffee went into the air. Nothing was created or destroyed. But something has been irreversibly lost. The ability to extract useful work from the temperature difference is gone. While the coffee was hot and the air was cool, you could, in principle, have used that temperature difference to drive a tiny heat engine. The hot coffee could have served as the hot reservoir, the room air as the cold reservoir, and you could have extracted work from the flow of heat between them. Not all the heat, but some of it. Now that the coffee and the air are at the same temperature, that opportunity has vanished. The energy is still there. Every unit of heat that left the coffee is now in the air. But it's spread out. It's at a uniform temperature. And a uniform temperature means no temperature difference. And no temperature difference means no ability to drive a heat engine. The energy has become useless for doing work. Entropy has increased. The universe has moved one step further in the direction it always moves. And here's the point that makes this truly universal. This isn't just about coffee and engines. This happens in every physical process where energy moves or transforms. When you charge your phone, some electrical energy becomes waste heat in the charging cable. When your body digests food, chemical energy from nutrients gets partly converted to body heat that radiates away. When sunlight hits a solar panel, some energy generates electricity and some becomes heat in the panel itself. Every single energy conversion in every physical system you can name degrades some energy from a useful form to a less useful form. Every single one increases the total entropy of the universe. There are no exceptions, and there are no refunds. This raises a natural question. If every process increases entropy, if every energy transformation wastes some quality, then where does it all end? If entropy relentlessly increases and the quality of energy relentlessly decreases, what happens when there's no quality left? What happens when every temperature difference has equalized, when every concentration gradient has flattened, when every bit of energy in the universe has been dispersed into thin, lukewarm, useless heat? That question has an answer, and it's one of the most sobering conclusions in all of physics. But we'll come to it later. For now, let's make sure the connection between the two pictures of entropy is completely clear. We've been talking about entropy in two different languages. The statistical language, where entropy counts microstates, and the thermodynamic language, where entropy tracks heat flow and energy degradation. These aren't two different things. They're two views of exactly the same thing. When heat flows from hot to cold, that's molecules sharing kinetic energy through random collisions, and the spread-out distribution has overwhelmingly more microstates. When an engine wastes heat, that's concentrated, organized energy dispersing into random molecular motion, and the dispersed state has overwhelmingly more microstates. When a temperature difference equalizes, that's the system settling into the macrostate with the largest number of compatible microstates, because that's the state it's most likely to find itself in by pure statistics. The thermodynamic definition of entropy, the one Clausius developed, talks about heat transfer and temperature. If you transfer a small amount of heat at a high temperature, entropy increases a little. If you transfer that same amount of heat at a low temperature, entropy increases a lot. This is why dumping waste heat into a cold reservoir creates more entropy than absorbing heat from a hot source reduces it. In any real process, the entropy created by dumping heat always exceeds the entropy consumed by absorbing it. The books never balance. There's always a surplus. And that surplus is the irreversible increase in the universe's entropy. Boltzmann's statistical definition, S equals K log W, explains why Clausius's rule works. High temperature means molecules are moving fast with lots of kinetic energy. The number of microstates is already large. Adding a bit more energy opens up relatively few additional microstates because there are already so many available. Low temperature means molecules are moving slowly with little kinetic energy. The number of microstates is comparatively small. Adding the same bit of energy opens up a relatively large number of new microstates because the system had fewer to begin with. So transferring heat from a hot object to a cold one increases the cold object's microstate count by more than it decreases the hot object's count. The total number of microstates for the combined system goes up. Entropy increases. The two pictures, Clausius's heat flow and Boltzmann's microstate counting, agree perfectly. They're the same truth expressed in different vocabularies. There's one more crucial idea to absorb before we move on. It's the concept of irreversibility, and it's central to everything entropy does in the physical world. A process is reversible if you can run it backward and return everything. the system and its surroundings to exactly the state they started in. A process is irreversible if you cannot. If running it backward would require something that doesn't happen spontaneously. Almost every process you encounter in daily life is irreversible. A ball bouncing on the floor comes to rest as its kinetic energy converts to heat through friction and deformation. You never see a ball sitting on the floor suddenly leap into the air, gathering heat from its surroundings and converting it into kinetic energy. A drop of ink in a glass of water spreads until the water is uniformly colored. You never see uniformly colored water spontaneously concentrate its ink back into a single drop. An egg falls and shatters. The shattered egg never reassembles. In every case, the forward process increases entropy. The reverse process would decrease entropy. And decreasing entropy is so overwhelmingly improbable that it simply doesn't happen. Notice what this means. The laws of physics at the microscopic level, Newton's laws, quantum mechanics, electromagnetism, are all time reversible. If you filmed a single molecule bouncing off another and played the film backward, the reversed collision would be perfectly valid physics. Nothing about the reversed version would violate any law. But when you have trillions of molecules, the forward process increases entropy and the reverse doesn't happen. The irreversibility isn't in the laws, it's in the statistics. It emerges when you go from a handful of particles to an astronomical number. Individual molecular events are reversible. Collective behavior is not. And this is perhaps the most startling thing about entropy. It creates a distinction between past and future that doesn't exist in the fundamental equations. The microscopic laws of physics don't know which direction time flows. They work equally well forward and backward. But entropy stamps a direction onto physical processes. Things that increase entropy happen. Things that decrease entropy don't. Before becomes different from after. The past becomes different from the future. And that difference, that arrow pointing from low entropy to high entropy, is the only reason the past feels different from the future at all. Every time you break an egg, every time you stir cream into coffee, every time you breathe and convert ordered chemical energy into diffuse body heat, you are experiencing the second law of thermodynamics in action. You are riding the one-way current of entropy from less probable to more probable, from fewer microstates to more microstates, from usable energy to unusable energy. And the current never reverses. Not because it can't in principle, but because the universe has so many particles and so many possible arrangements, the statistics become absolute. The second law is not a rule imposed by some cosmic authority. It is the deepest consequence of counting, of recognizing that when you have enough pieces, the most likely outcome isn't just likely, it is certain. And that certainty shapes everything. The flow of heat, the waste in every engine, the cooling of every star, the aging of every living thing. It shapes the very direction of time itself. And it is in that direction, that arrow, that we now turn. We ended with a profound claim. Entropy stamps a direction onto physical processes, a direction that the fundamental laws of physics, taken on their own, do not possess. This sounds almost paradoxical. How can a direction emerge from laws that have no direction? How can the universe pick out a past and a future when the equations governing individual particles work equally well in either direction? This question has haunted physicists for over a century. It sits at the intersection of thermodynamics, cosmology, and the philosophy of time itself. And the answer, when you trace it carefully, leads to one of the most astonishing facts about the universe we live in. Let's start with the puzzle in its sharpest form. Take any fundamental law of physics, Newton's laws of motion, Maxwell's equations of electromagnetism, the equations of quantum mechanics, even Einstein's general relativity. All of them are time symmetric. This means that if you take any process governed by these laws and play it in reverse, the reversed version is also a perfectly valid process. A planet orbiting a star clockwise is just as valid as the same planet orbiting counterclockwise. An electron emitting a photon and recoiling is just as valid, run backward, as an electron absorbing a photon and accelerating. At the level of individual particles and individual interactions, the laws of physics do not distinguish between forward and backward in time. Past and future are interchangeable. The equations don't know the difference. And yet, you know the difference. You know it every moment of your life. You remember yesterday, but not tomorrow. Eggs break, but never unbreak. Coffee cools, but never spontaneously heats up. You age. You can't unage. The world around you is saturated with processes that go one way and never the other. There is an unmistakable arrow pointing from past to future, and that arrow is so deeply woven into your experience that you barely notice it. But it's there, and it needs an explanation, because the microscopic laws don't provide one. If every individual molecular interaction is reversible, why is the macroscopic world so stubbornly irreversible? The answer, as we've been building toward, is entropy. The arrow of time is the direction of increasing entropy. The reason the past feels different from the future, the reason causes precede effects, the reason memory works the way it does, all of it traces back to the statistical asymmetry between low entropy and high entropy states. Processes that increase entropy happen constantly and naturally. Processes that decrease entropy are so wildly improbable that they never occur in practice. This one-way statistical drift is what gives time its direction. But saying entropy increases just pushes the question back one step. Why does entropy increase toward the future rather than toward the past? If the microscopic laws are time symmetric, then the statistical arguments should work equally well in both directions. If a system is in a medium entropy state right now, the overwhelming number of microstates compatible with that condition would lead to higher entropy in the future, yes. But by the exact same statistical reasoning, the overwhelming number of microstates would also imply higher entropy in the past. The math doesn't care which direction you call forward. Run the statistics backward, and you'd predict that the system was at higher entropy 5 minutes ago, and just happened to fluctuate down to its current state. That prediction is almost certainly wrong. 5 minutes ago, the coffee was hotter, the ice cube was bigger, entropy was lower. But the statistics, applied blindly in both directions, would predict higher entropy in both directions, past and future. Something is missing from the statistical argument alone. This problem was first identified in the 1870s by Joseph Loschmidt, a colleague of Boltzmann's in Vienna. Loschmidt pointed out that if the microscopic laws are time reversible, then for every sequence of molecular motions that increases entropy, there exists an equally valid sequence that decreases it. Just reverse all the velocities. Every molecule goes backward along its path. Every collision undoes itself. Entropy decreases. The reversed motion is a perfectly valid solution to the laws of physics, so why do we only see entropy increasing? Boltzmann struggled with this objection. It struck at the heart of his statistical framework. If the laws of physics are symmetric in time, how can entropy have a preferred direction? The answer that physicists have gradually converged on over the past century is both simple and staggering. Entropy increases toward the future because it was much, much lower in the past. The arrow of time doesn't come from the laws of physics themselves, it comes from the initial conditions of the universe. The universe began in a state of extraordinarily low entropy, and everything that has happened since, every cooling star, every crumbling mountain, every aging body, every thought you have ever had, is part of the long, slow, statistically inevitable unfolding from that low entropy beginning toward higher and higher entropy. This idea is sometimes called the past hypothesis, a term coined by the philosopher David Albert, though the insight goes back to Boltzmann himself and was developed extensively by physicists like Roger Penrose. The past hypothesis states, simply, that the universe started in a very special, very low entropy state. Given that starting point, the second law follows naturally. If you begin with low entropy, the overwhelming majority of possible evolutions lead to higher entropy. The universe doesn't need a special law to push entropy upward. It just needs a special starting point at the bottom. Think of it like a ball placed at the top of a hill. The laws of physics don't contain a special rule that says balls roll downhill. They say balls accelerate in the direction of gravitational force. A ball at the top of a hill will roll down, not because of a one-way law, but because of where it started. If the ball had started at the bottom of the valley, it would just sit there. The downhill motion isn't built into the laws, it's built into the initial conditions. Similarly, the increase of entropy isn't built into the fundamental laws of physics, which are time-symmetric. It's built into the fact that the universe started in an exceptionally low entropy configuration. Given that starting point, the rest follows from statistics. But what does it mean for the early universe to have low entropy? The universe right after the Big Bang was incredibly hot and dense, a plasma of particles at temperatures of trillions of degrees, filling all of space almost uniformly. That sounds chaotic, disordered, like a high entropy state. And in terms of the matter and radiation, it was high entropy. The particles were spread out as uniformly as possible, in thermal equilibrium, with maximum randomness in their motions. So where was the low entropy? The answer is gravity. When gravity is important, and at the scale of the universe, gravity is the dominant force, uniform distribution is not the high entropy state, it's the low entropy state. This is deeply counterintuitive, and it's one of the places where the naive disorder equals entropy picture fails most spectacularly. For a gas in a box, uniform distribution is the high entropy state. Spread the gas out evenly, and you've maximized the number of microstates. But add gravity to the picture, and everything changes. Gravity is attractive. It pulls matter together. A uniform distribution of matter in a gravitational system is unstable. It's like a ball balanced on a hilltop. Given time, gravity will cause the uniform matter to clump. Small density fluctuations grow. Regions slightly denser than average attract more matter, becoming denser still. Clouds of gas collapse into stars. Stars cluster into galaxies. Galaxies cluster into filaments and walls. The clumpy, structured universe we see today, with stars and galaxies and vast empty voids, is actually higher entropy than the smooth, uniform early universe. To understand why, think about what gravity does to the microstate counting. Earlier, we imagined gas molecules in a box. Gravity was irrelevant in that picture. The molecules bounced around freely, and the state with the most microstates was the one where molecules were spread evenly throughout the box. Concentrating them in one corner reduced the number of accessible arrangements. Spreading them out increased it. But gravity changes the game entirely, because gravity is attractive. It pulls matter together, and when matter clumps under gravity, new degrees of freedom become available that didn't exist before. Consider a vast, perfectly uniform cloud of hydrogen gas filling a region of space. Every part of the cloud is the same temperature, the same density, the same pressure. It looks like the maximum entropy state because it's uniform, spread out, featureless. But gravitationally, this configuration is unstable. A slight overdensity in one region pulls surrounding gas inward. As the gas falls inward, it accelerates. Gravitational potential energy converts into kinetic energy. The infalling gas heats up. Collisions between gas molecules become more violent. The gas can begin to radiate light, sending photons streaming outward in every direction. Each photon carries energy away from the collapsing region, and each photon represents additional microstates, additional ways the energy can be distributed. Before the collapse, all the energy was locked in the uniform gravitational configuration of the cloud. After the collapse begins, that energy is being shared between the kinetic motion of the gas, the thermal radiation pouring outward, and the deeper gravitational potential well at the center. The system has access to enormously more microscopic arrangements than it did when everything was smooth and uniform. Take this further. The collapsing cloud fragments. Multiple clumps form. Each clump collapses independently, heats up, and eventually ignites nuclear fusion. Now you have stars, blazing points of light pouring photons into the surrounding space. Every photon emitted is another microstate. Every variation in temperature between the hot stellar core and the cold surrounding void is another way energy can be distributed. The clumpy, star-filled universe has access to vastly more microstates than the smooth, featureless cloud it came from. And the ultimate gravitational clump, a black hole, has the highest entropy of all, as we will see. Gravity doesn't just rearrange matter. It unlocks entirely new categories of microstates that simply don't exist when matter is uniformly distributed. That is why the smooth early universe was low entropy even though it looked disordered, and why the structured universe we see today, full of stars and galaxies and temperature gradients, is higher entropy even though it looks ordered. This seems backward. Stars and galaxies look ordered. They have structure, shape, organization. The early universe, a featureless hot soup, looks disordered. But entropy doesn't care about appearances. It cares about microstates. And when you account for gravity, a clumpy universe with stars and black holes has access to far more microstates than a smooth, uniform one. The clumpy universe is where the statistics point. The smooth, early universe was special, improbable, low entropy. And the entire history of cosmic structure, the formation of galaxies and stars and planets, is the universe's entropy increasing as gravity does its work. Roger Penrose has estimated just how special the early state was. He calculated the probability of the universe starting in a configuration as low entropy as the one we observe, and the number he arrived at is staggering. The odds are roughly 1 in 10 to the power of 10 to the 123rd. That's not 10 to the 123rd, that's 10 raised to a power that itself has 123 digits. It is a number so incomprehensibly vast that there is no way to visualize it, no analogy that comes close, no comparison that works. The early universe was not just somewhat special. It was special to a degree that defies every available superlative. And we do not know why. This is one of the deepest unsolved problems in physics. Why did the universe begin in such a low entropy state? The past hypothesis tells us that it did, and the second law follows as a consequence. But the past hypothesis itself is unexplained. It's a brute fact, an initial condition that we observe but cannot yet derive from any deeper principle. Some physicists, including Penrose, have proposed theories to explain it. Penrose's conformal cyclic cosmology suggests that the universe goes through infinite cycles, and the apparent low entropy of the Big Bang is actually the high entropy end state of a previous cycle, reinterpreted through a mathematical transformation. Others appeal to inflationary cosmology, suggesting that a period of rapid expansion in the first fraction of a second smoothed out the universe and set up the low entropy initial conditions. But none of these explanations are settled. The origin of the arrow of time remains an open question, one of the most important in all of science. What we do know is that once you accept the past hypothesis, everything falls into place. The universe began in a low entropy state. Since then, entropy has been increasing. This increase is what gives time its direction. It's why we remember the past but not the future. Because memories are physical records, low entropy structures created by processes that increase entropy elsewhere. It's why causes precede effects, because the causal chain runs in the direction of increasing entropy. It's why you can turn an egg into scrambled eggs, but not the reverse, because scrambling increases entropy and unscrambling would decrease it. The arrow of time is not a separate law. It is entropy's shadow, cast across everything that happens. Now, let's address something that seems to contradict all of this. If entropy always increases, if the universe is sliding inexorably from order to disorder, from concentrated energy to dispersed energy, then how do you explain the existence of, well, anything interesting? How do you explain snowflakes? How do you explain crystals growing in perfect geometric lattices? How do you explain a refrigerator, a machine that moves heat from cold to hot, apparently in blatant violation of the second law? And most profoundly, how do you explain life? Living organisms are staggeringly complex, highly organized structures. A single cell contains molecular machinery of breathtaking precision. DNA encodes information with extraordinary fidelity. Your body maintains a constant temperature, repairs damage, fights off invaders, and builds new tissue from raw materials. All of this looks like decreasing entropy. It looks like order emerging from disorder. It looks like the second law being broken every second of every day, inside every living thing on Earth. But it's not being broken, not even slightly, and understanding why is essential to understanding what entropy really means. The key is a single word that people often overlook when stating the second law: isolated. The second law says that the entropy of an isolated system never decreases. An isolated system is one that exchanges nothing with its surroundings. No energy in, no energy out. No matter in, no matter out. It's a sealed box, completely cut off from the rest of the universe. For such a system, entropy can only increase or stay the same. But almost nothing in the real world is isolated. Your cup of coffee isn't isolated. It exchanges heat with the surrounding air. Your body isn't isolated. You eat food, breathe air, radiate heat, and excrete waste. The Earth isn't isolated. It receives energy from the sun and radiates energy back into space. A refrigerator isn't isolated. It's plugged into the wall, consuming electrical energy and dumping heat out the back. When a system is not isolated, when it exchanges energy or matter with its surroundings, its entropy can decrease locally. You can create order in one place as long as you create more disorder somewhere else. The total entropy of the system plus its surroundings still increases. The second law holds for the whole picture, but within that picture, local pockets of decreasing entropy are not just allowed, they're common. They happen everywhere. They're how the universe builds interesting things. A refrigerator is the clearest example. The inside of your refrigerator is cold. The kitchen is warm. Heat naturally flows from hot to cold, from the kitchen toward the fridge interior. But the refrigerator reverses this. It pumps heat from the cold interior to the warm kitchen, making the inside colder and the kitchen warmer. This locally decreases entropy inside the fridge. Heat is being concentrated, moved from a region where molecules are already slow to a region where they're already fast. That's the wrong direction for spontaneous heat flow. But the refrigerator isn't doing this for free. It's consuming electrical energy. The compressor does work on a refrigerant fluid, compressing it, heating it up, allowing it to dump heat into the kitchen, then expanding it and cooling it down to absorb heat from the fridge interior. The electrical energy that powers this cycle came from a power plant, which burned fuel or split atoms or captured sunlight. At every step, entropy was generated. The entropy decrease inside the fridge is more than compensated by the entropy increase in the power plant, the transmission lines, the compressor motor, and the warm air behind the fridge. Add it all up, and the total entropy of the universe has increased, even though one small region got colder and more ordered. Let's look at a few more everyday processes through this lens, because they reveal just how universal this pattern is. Consider something as simple as mixing cream into coffee. You pour a splash of cream and watch it swirl through the dark liquid. At first, you can see streaks and tendrils of white curling through the brown. After a few seconds, maybe a stir or two, the coffee is uniformly tan. The cream and coffee have mixed. Now ask yourself, have you ever seen the reverse happen? Have you ever watched a cup of tan coffee spontaneously separate into a layer of cream floating on top of black coffee? Of course not. But why not? No fundamental law forbids it. Every molecule of cream is still in the cup. Every molecule of coffee is still there. The forces between molecules are perfectly reversible. Any individual collision between a cream molecule and a coffee molecule could run backward without violating physics. The reason mixing is irreversible is pure statistics. When the cream is concentrated in one region and the coffee in another, the system is in a very specific, very low entropy arrangement. The molecules of cream are all near each other, and the molecules of coffee are all near each other. There are relatively few microstates compatible with that separated condition. But when the cream is evenly distributed throughout the coffee, the molecules could be in an enormous number of different positions. Any cream molecule could be anywhere in the cup. The number of microstates corresponding to uniform mixing is so astronomically larger than the number corresponding to separation that random molecular motion carries the system toward the mixed state with absolute statistical certainty. To unmix spontaneously, every cream molecule would need to happen to wander back into the same corner of the cup simultaneously. The probability of that happening is effectively zero, for the same reason that all the air in a room never spontaneously gathers in one corner. The numbers are simply too vast. Diffusion is the same story. Open a bottle of perfume in one corner of a room. Within minutes, you can smell it everywhere. The perfume molecules, initially concentrated near the bottle, have spread throughout the room through random collisions with air molecules. Each molecule bounces around randomly, colliding billions of times per second, drifting gradually away from the high concentration region toward lower concentration regions. There's no force pulling them outward. They're just wandering randomly. But because there are so overwhelmingly more arrangements where the perfume molecules are spread out than arrangements where they're all clustered near the bottle, random wandering inevitably produces spreading. Diffusion is entropy in action. The molecules aren't obeying a command to spread out. They're exploring the landscape of possible positions, and the spread out landscape is incomprehensibly larger than the concentrated one. Chemical reactions follow the same logic. When iron rusts, iron atoms on the surface combine with oxygen molecules from the air to form iron oxide. The chemical bonds in iron oxide are lower energy than the separate iron and oxygen bonds. The excess energy is released as heat, warming the surroundings slightly. The heat disperses into the environment, spreading among air molecules, the ground, everything nearby. The entropy of the surroundings increases. Could the rust spontaneously reverse? Could iron oxide pull heat from the environment, concentrate it, use it to break the iron-oxygen bonds, and release pure iron and oxygen gas? Energetically, it's conceivable if you could gather enough ambient heat. But the heat has dispersed among trillions of air molecules. Reconcentrating it would require those molecules to spontaneously coordinate their random motions and funnel energy back into the rust. The probability of that spontaneous coordination is, once again, effectively zero. This is the practical meaning of energy quality that makes entropy so consequential for everything from engineering to biology to economics. When we say we're running out of energy, we don't mean the universe is losing energy. energy is strictly conserved. What we mean is that we're running out of low entropy energy, energy in concentrated, usable forms. Every barrel of oil, every chunk of coal, every kilogram of uranium fuel contains energy stored in organized chemical or nuclear bonds. When we burn the oil or split the uranium, we extract work, but we also disperse energy as waste heat into the environment. The total energy is unchanged, but the concentrated, useful portion has shrunk, and the dispersed, useless portion has grown. We've moved energy down the quality ladder, from low entropy to high entropy. Fossil fuel reserves aren't tanks of energy that get emptied. They're reservoirs of low entropy that get spent. The energy remains in the universe forever. The ability to use it does not. This is why a perpetual motion machine is impossible. Not because we lack clever enough engineers, but because the entropy cost of every energy conversion means some useful capacity is always lost. Every machine that runs consumes low entropy input and produces high entropy waste. Even a perfectly efficient machine, if such a thing could exist, would at best break even on entropy. In practice, every real machine produces more entropy than the theoretical minimum. The waste builds up, the gradients flatten, the useful energy diminishes. And no amount of ingenuity can reverse that arithmetic, because the arithmetic is counting microstates, and microstates don't negotiate. The same principle applies to every example of local order. A crystal growing from a solution looks like entropy decreasing. Atoms that were randomly dissolved in liquid arrange themselves into a perfect lattice. But crystallization releases heat, the latent heat of fusion. That heat flows into the surrounding liquid, increasing its entropy. The entropy decrease of the crystal is more than offset by the entropy increase of the surroundings. The total entropy goes up. A plant growing from a seed looks like entropy decreasing. A small, simple seed becomes a large, complex organism with specialized tissues and structures. But the plant is powered by sunlight. It absorbs high-quality, low-entropy photons from the sun and emits low-quality, high-entropy infrared radiation back into the cold darkness of space. The same thermodynamic arithmetic that applies to a leaf applies to the entire planet. Concentrated energy comes in, dispersed energy goes out. The total is balanced. But the entropy of the outgoing radiation is vastly higher than the entropy of the incoming sunlight, and in that gap between arrival and departure, the entire biosphere operates. The plant has taken concentrated energy from the sun and dispersed it into many more low-grade photons. It has increased entropy in the process of building its own ordered structure. The plant doesn't defy the second law. It exploits the entropy gradient between the hot sun and the cold sky to build local order while increasing total entropy. And this brings us to life itself. Because life is not a violation of the second law, life is perhaps the most spectacular manifestation of the second law in action. Living organisms are entropy-generating machines of extraordinary sophistication. Your body maintains a constant internal temperature of about 37 degrees Celsius. It repairs damaged cells. It synthesizes complex proteins from simple amino acids. It maintains ion gradients across cell membranes. It stores information in DNA with error correction mechanisms that would impress any computer engineer. All of this requires energy, and all of this generates entropy. You eat food. Food contains chemical energy stored in complex organic molecules, sugars, fats, proteins. These molecules are low entropy, highly ordered arrangements of atoms. Your body breaks them down through digestion and cellular respiration. It extracts the energy stored in chemical bonds and uses it to power everything you do: thinking, moving, growing, repairing. But in the process, it converts those ordered molecules into simple waste products: carbon dioxide, water, urea. It releases heat into the surroundings. The waste products and heat represent higher entropy than the original food. For every bit of order your body creates internally, it creates even more disorder externally. You are a machine that takes in low entropy matter and energy and pumps out high entropy waste and heat. Follow a single meal through your body and you can watch entropy in action at every step. You eat an apple. The apple contains sugars, primarily glucose, molecules assembled by the apple tree using energy from sunlight. Those glucose molecules are beautifully ordered structures: 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms arranged in a precise ring. The chemical bonds holding that ring together store energy. Energy that the tree captured from low entropy solar photons and locked into molecular architecture. That stored energy is what makes the apple food rather than just matter. Your digestive system breaks the apple down, separating the glucose from the fiber, the vitamins, the water. The glucose enters your bloodstream and reaches your cells. Inside each cell, a process called cellular respiration dismantles the glucose molecule step by step. The cell doesn't just smash the molecule apart. It carefully extracts energy from each bond through a long chain of chemical reactions, transferring that energy to molecules of ATP, the universal energy currency of living cells. ATP powers almost everything your cells do: building proteins, contracting muscles, transmitting nerve signals, copying DNA. But here is where the entropy accounting becomes vivid. You started with 1 glucose molecule and 6 oxygen molecules. You end with 6 carbon dioxide molecules and 6 water molecules. Count the atoms. They're all still there. Nothing has been created or destroyed. The total energy is conserved. But the entropy has increased enormously. The carbon atoms that were locked in a single ordered ring structure are now scattered across 6 separate carbon dioxide molecules, each one drifting independently through your bloodstream, eventually exhaled into the atmosphere. The hydrogen atoms that were part of the glucose ring are now bound in water molecules dispersed throughout your body. The energy that was concentrated in specific chemical bonds has been partially captured in ATP and partially released as heat, warming your tissues, radiating from your skin into the surrounding air. Each ATP molecule, when it delivers its energy, becomes ADP, a lower energy molecule, and releases heat in the process. More entropy. By the time the apple's energy has been fully used, every bit of the original concentrated, ordered chemical energy has been converted into diffuse body heat, radiating away into your environment. The carbon has been exhaled as gas. The water has been perspired or exhaled or excreted. The ordered structure of the apple is gone. Its atoms persist, scattered across the atmosphere and the environment, but the organization, the low entropy arrangement that made it food, has been irreversibly dispersed. You extracted the order you needed to stay alive, and you paid for it by spreading disorder into the world around you. Your body recycles roughly its own weight in ATP every single day, tens of kilograms of the molecule built and spent and rebuilt again, across roughly 37 trillion cells, each one a microscopic entropy engine running continuously from the moment you're born until the moment you die. The physicist Erwin Schrödinger captured this beautifully in his 1944 book, What is Life? He described living organisms as feeding on negative entropy, or what he called neg entropy. By this he meant that living things maintain their internal order, not by violating the second law, but by constantly importing low entropy resources from their environment and exporting high entropy waste. A living organism is like a whirlpool in a river. The whirlpool maintains its structure, its order, its recognizable form, but only because water is constantly flowing through it. Stop the flow and the whirlpool vanishes. Similarly, stop the flow of low entropy energy through a living organism, stop feeding it, stop letting it breathe, and its internal order collapses. It dies. Its complex molecules break down. Its structure decays. It returns to equilibrium with its surroundings. Entropy has its way. The Earth itself operates on this principle. Our planet receives high-quality, low-entropy energy from the Sun in the form of visible light. Photons from the Sun are energetic and concentrated. The Sun's surface temperature is about 5,500 degrees Celsius, and the photons it emits carry substantial energy per photon. The Earth absorbs this energy, uses it to drive weather systems, ocean currents, photosynthesis, and all the complex processes of the biosphere. Then the Earth radiates energy back into space as infrared radiation. The temperature of this outgoing radiation is much lower, about -18 degrees Celsius on average. Because the outgoing photons are lower energy, the Earth must emit many more photons than it absorbs to maintain energy balance. For every high-energy photon coming in from the Sun, roughly 20 lower-energy photons go out into space. Same total energy, but far more photons, far more microstates, far higher entropy. Life doesn't fight entropy. Life rides entropy. Life exploits the difference between the hot sun and the cold darkness of outer space. Without that difference, without the gap between a hot source and a cold sink, there would be no gradient to exploit, no energy flow. No weather, no photosynthesis, no life. The sun doesn't just give us energy, it gives us low entropy energy, and that distinction makes all the difference. This pattern repeats at every scale. Stars are entropy engines. A star takes a cloud of hydrogen, a relatively low entropy gravitational configuration, and converts it into helium, photons, neutrinos, and eventually heavier elements. Every fusion reaction in the star's core increases the total entropy of the universe. The star shines because entropy is increasing. Galaxies are entropy engines. Rivers are entropy engines. Hurricanes are entropy engines. Every organized structure in the universe, from a spiral galaxy to a snowflake to a bacterium, exists because it sits in the flow between a low entropy source and a high entropy sink, extracting useful work from the gradient while pumping entropy into its surroundings. So the next time someone tells you that life violates the second law, or that evolution contradicts entropy, or that the existence of complex structures proves entropy wrong, you'll know the answer. These claims confuse local entropy with total entropy. Yes, a living cell is more ordered than the raw materials it's made from. Yes, a crystal is more organized than the solution it grew from. Yes, a star is more structured than the gas cloud that collapsed to form it. But in every single case, the local decrease in entropy is paid for by a larger increase elsewhere. The universe's total entropy goes up. The second law holds without exception. This understanding transforms how you see the world around you. Every process you witness, every event in your daily life, is part of the great entropic unfolding that began with the low entropy Big Bang and continues today. The coffee cooling on your desk, the rusting of iron, the growth of a child, the decay of a fallen tree, the burning of a candle, all of these are entropy increasing. All of these are the universe exploring its vast landscape of possible microstates, moving statistically from less probable arrangements to more probable ones. And the arrow of time, the thing that makes the past feel different from the future, that makes memory possible, that gives your life a narrative direction from birth to death, that arrow is nothing more and nothing less than the direction in which entropy increases. It points from the extraordinary, improbable, low entropy beginning of the universe toward the ordinary, probable, high entropy future. Every clock that ticks, every candle that burns, every thought you think is a step along that one-way path. Not because a cosmic law commands it, but because the starting point was so spectacularly unlikely, so far from equilibrium, that the universe has been statistically unwinding ever since. And it will keep unwinding. The arrow of time does not bend, it does not reverse, it does not pause. It flows in the direction of increasing entropy, from the special past toward the ordinary future, carrying everything with it. But how far does this unwinding go? What happens when the last temperature difference has equalized? When the last star has burned out? When every gradient has flattened and every pocket of useful energy has been dispersed into thin, cold radiation? What happens when entropy reaches its maximum? That question takes us to the ultimate fate of the universe, and to the deepest meaning of the phrase, "nothing escapes it." We've been building a picture of entropy as a statistical tide, an overwhelming drift towards states with more microscopic arrangements, driven not by a force, but by the sheer weight of probability. We've seen how it gives time its direction, how it governs the flow of heat, how it permits local pockets of order only because they export even greater disorder elsewhere. But now we need to push the picture to its ultimate consequences. Because if entropy really does govern the direction of everything, if nothing genuinely escapes it, then we need to follow the logic all the way to the end. To black holes, to the far future of the cosmos, and to the final, silent state where entropy has nothing left to increase toward. Let's begin with the most extreme objects in the known universe, black holes. For decades, black holes seem to pose a problem for entropy. A black hole forms when a massive star exhausts its nuclear fuel and its core collapses under its own gravity. The matter falls inward, concentrating into a region so small and so dense that the escape velocity exceeds the speed of light. Nothing can get out. Not matter, not radiation, not information. The boundary of this region is called the event horizon, a surface of no return. Cross it, and you're falling inward forever. Now, here's the problem that troubled physicists in the early 1970s. Imagine you take a box of hot gas, a system with a known, calculable entropy, and you throw it into a black hole. The gas crosses the event horizon and vanishes. The entropy it carried seems to disappear. The universe outside the black hole has lost entropy. If nothing inside the black hole can communicate with the outside, then, as far as the external universe is concerned, that entropy is gone. The second law appears to be violated. You could, in principle, reduce the entropy of the observable universe simply by throwing things into black holes. A young physicist named Jacob Bekenstein, then a graduate student working under John Wheeler at Princeton, proposed a radical solution in 1972 and 1973. He argued that black holes themselves carry entropy, enormous amounts of it, and the entropy of a black hole is proportional not to its volume, as you might expect, but to the area of its event horizon. Specifically, the entropy is proportional to the surface area of the event horizon, measured in units of the Planck area, a tiny square with sides equal to the Planck length, about 1.6 times 10 to the negative 35 meters. The formula is remarkably simple. The entropy equals 1/4 of the event horizon area divided by the Planck area, multiplied by Boltzmann's constant. When you throw matter into a black hole, the black hole's mass increases. Its event horizon grows. And because its entropy is proportional to the area of that horizon, its entropy increases. Bekenstein showed that the entropy gained by the black hole always equals or exceeds the entropy of whatever fell in. the second law is saved. Entropy doesn't disappear when you throw things into a black hole. It gets transferred to the black hole itself, encoded somehow on the event horizon. Stephen Hawking was initially skeptical of Bekenstein's proposal, but when Hawking applied quantum mechanics to the region near a black hole's event horizon, he discovered something astonishing. Black holes are not perfectly black. They emit radiation. A faint thermal glow, now called Hawking radiation. The radiation has a temperature, and that temperature is inversely proportional to the black hole's mass. Small black holes are hot. Large black holes are cold. A black hole with the mass of our Sun would have a temperature of about 60 billionths of a degree above absolute zero, far colder than the cosmic microwave background radiation that fills space. But the temperature is real. The black hole is a thermal object with a well-defined temperature, and Bekenstein's entropy formula turned out to be exactly right. The numbers are staggering. A black hole with the mass of the Sun has an entropy of roughly 10 to the 77th in natural units. For comparison, all the matter and radiation in the observable universe, excluding black holes, has a total entropy of roughly 10 to the 88th. That's enormous. But the supermassive black holes at the centers of galaxies dwarf even that. The black hole at the center of the Milky Way, Sagittarius EYY star, has a mass of about 4 million times the mass of our Sun. Its entropy is vastly higher, roughly 10 to the 90th, and the supermassive black hole at the center of the galaxy M87, with a mass of about 6.5 billion solar masses, has an entropy that makes even Sagittarius EYY star look modest. When you add up the entropy of all the black holes in the observable universe, the total is estimated at around 10 to the 104th power. That single number dominates the entropy budget of the entire cosmos. The entropy of all the stars, all the gas, all the radiation, all the planets, all of it combined, is a rounding error compared to the entropy locked in black holes. This reveals something profound about where the universe's entropy actually resides. It's not in the heat of stars. It's not in the thermal glow of the cosmic microwave background. It's overwhelmingly in black holes. The most ordered-looking objects in the universe, featureless spheres defined by just 3 numbers, mass, charge, and spin, turn out to be the highest entropy objects that exist. They contain more hidden microscopic information, more possible internal configurations, than anything else in the cosmos. This is a stunning inversion of the naive disorder picture. A black hole looks simple, smooth, featureless. It's the opposite of what most people would call disordered. And yet it has more entropy than a galaxy full of stars and gas and dust and turbulence and chaos. Entropy is not disorder. Entropy counts microstates. And black holes, for reasons we still don't fully understand at a quantum level, have more microstates than anything else. The fact that black hole entropy scales with surface area rather than volume is itself one of the most important clues we have about the deep structure of space-time. In ordinary physics, the number of possible states of a system scales with its volume. A box twice as big should be able to hold twice as many configurations. But black holes violate this expectation. Their entropy scales with area, as though all the information about the black hole's internal state is somehow encoded on its 2-dimensional surface, rather than in its 3-dimensional interior. This observation led to the holographic principle, proposed by Gerard 't Hooft and developed by Leonard Susskind in the 1990s. The holographic principle suggests that the maximum amount of information that can be contained in any region of space is proportional to the area of its boundary, not its volume. This would mean that in some deep sense, the 3-dimensional universe we experience is a projection, a hologram, of information stored on a 2-dimensional surface. This idea remains speculative and hotly debated, but it emerged directly from thinking about entropy and black holes. The deepest questions about space, time, and information trace back to the same quantity we've been discussing all along. Now, let's follow entropy to the end of the universe. If entropy always increases, if every process degrades energy from useful forms to useless forms, if every temperature difference eventually equalizes, and every gradient eventually flattens, then the universe is heading toward a state of maximum entropy. A state where no further macroscopic change is possible, no temperature differences, no pressure gradients, no chemical reactions, no energy available to do work of any kind. This is the heat death of the universe, and it is, as far as current physics can tell, the most probable long-term fate of the cosmos. The timeline of this unwinding is almost incomprehensible. It stretches across eras so vast that the current age of the universe, 13.8 billion years, is barely a prologue. And alongside the slow entropic running down of matter and starlight, something else is happening. The expansion of the universe continues, driven by dark energy. Space stretches. Galaxies that are not gravitationally bound to each other drift apart. Over billions of years, the observable universe will shrink from our perspective. Galaxies beyond a certain distance will be carried away faster than their light can reach us. The night sky, already mostly dark, will grow darker still. Eventually, our local group of galaxies, gravitationally bound together, will merge into a single large elliptical galaxy. And beyond that merged galaxy, the sky will be empty. Every other galaxy will have receded beyond the cosmic horizon, carried away by the expansion of space, invisible and unreachable forever. But the story of entropy's final victory plays out not just in the expanding distance between galaxies, it plays out in the fate of every structure within them. The last holdouts will be the black holes. Supermassive black holes with masses of millions or billions of solar masses will persist for extraordinary lengths of time. But even black holes are not eternal. Hawking radiation ensures that every black hole, no matter how massive, slowly loses mass. The process is fantastically slow for large black holes. A black hole with the mass of the Sun would take roughly 10 to the 67th years to evaporate. A supermassive black hole might take 10 to the 100th years, a number called a googol. That is a 1 followed by 100 zeros. For perspective, the current age of the universe is about 10 to the 10th years. The time for a supermassive black hole to evaporate is so much longer than the current age of the universe that the comparison is laughable. The current age of the cosmos is an infinitesimal blip compared to the timescale of black hole evaporation. Let's slow down and walk through these eras more carefully, because the timescales involved are so extreme that they deserve more than a passing mention. They reveal just how patient entropy really is. We live right now in what cosmologists call the stelliferous era, the age of stars. It began a few 100 million years after the Big Bang, when the first stars ignited, and it will continue for roughly another 100 trillion years. During this era, hydrogen gas collapses under gravity, nuclear fusion ignites, and stars shine. This is the era of light, of warmth, of the energy gradients that power everything we know. All of human history, all of biological evolution, all of Earth's existence fits comfortably within a thin sliver at the beginning of the stelliferous era. The universe is approximately 13.8 billion years old. The stelliferous era will last roughly 10,000 times longer than the universe has existed so far. We are living in the opening moments of the age of stars, not near its end. But the stelliferous era will end. Star formation requires cold, dense clouds of hydrogen to collapse. As galaxies exhaust their gas supply, fewer and fewer new stars are born. Meanwhile, existing stars burn through their fuel and die. Massive stars go quickly, living only millions of years. Sun-like stars last billions of years. But the smallest red dwarfs, stars with only about 8% the mass of the Sun, burn their hydrogen with such extreme frugality that they can last for trillions of years. These dim, slow-burning embers will be the last stars shining in the universe. For most of the stelliferous era, the universe will be dominated not by bright, hot stars like our Sun, but by these faint red specks, each one barely luminous enough to warm a close orbiting planet above freezing. A civilization living around such a star trillions of years from now would watch the sky grow emptier with each passing age, stars winking out one by one, never to be replaced, until the last red dwarf exhausted its hydrogen and cooled into a white dwarf. The universe would go dark. What follows is the degenerate era, lasting from roughly 10 to the 15th years to perhaps 10 to the 40th years after the Big Bang. During this vast span, the universe contains only stellar corpses. White dwarfs, neutron stars, and black holes drift through an expanding void. No fusion occurs anywhere. The only light comes from the faint thermal radiation of cooling white dwarfs, each one growing dimmer and colder over trillions of years. Occasionally, two white dwarfs in a binary system might spiral together and merge, briefly flaring into a supernova. But these events grow rarer and rarer as gravitational interactions scatter objects apart. During the degenerate era, the familiar structure of galaxies slowly dissolves. Stars within a galaxy interact gravitationally, exchanging energy through close encounters. Over immense timescales, some stars gain enough energy to escape the galaxy entirely, flung outward into intergalactic space. Others lose energy and spiral inward, eventually falling into the central supermassive black hole. The galaxy gradually evaporates from the outside in, losing stars to the void while feeding its central black hole. After roughly 10 to the 20th years, most galaxies will have dissolved. Their stars will be scattered lone wanderers drifting through the darkness, impossibly far from any neighbor. If protons are unstable, as some grand unified theories predict, then during the later stages of the degenerate era, atomic matter itself begins to disintegrate. Protons and neutrons inside every remaining white dwarf and neutron star decay into lighter particles, positrons, pions, photons. The process is fantastically slow. Each individual proton might survive for 10 to the 40th years on average, but given enough time, every proton in the universe will decay. White dwarfs will slowly evaporate from within, not by losing heat, but by losing matter itself. Their atoms will dissolve particle by particle over spans of time that make the current age of the universe seem like the blink of an eye. If protons are stable, then white dwarfs and neutron stars will persist far longer, but even they won't last forever. Quantum tunneling, the ability of particles to pass through energy barriers with a small but non-zero probability, ensures that even cold, dead stars will eventually undergo nuclear reactions. Given enough time, iron, the most stable nuclear configuration, will be the final product. And given still more time, quantum tunneling could even cause these cold iron spheres to collapse into black holes. The timescale for this might be 10 to the power of 10 to the 76th years, a number so absurdly large that it exists only as a mathematical concept, not as anything a human mind could visualize. But entropy is patient. It has all the time that will ever exist. After matter has decayed or collapsed, the universe enters the black hole era. Only black holes remain as organized structures. Everything else has dissolved into a thin bath of particles and radiation. The black holes sit in the void, slowly evaporating through Hawking radiation, each one losing mass, photon by photon, over timescales that stretch to the Google year mark and beyond. But eventually, every black hole will evaporate. The last one will shrink, grow hotter, radiate more intensely, and finally vanish in a burst of particles and radiation. And after that, there will be nothing left but a thin, cold soup of photons, neutrinos, electrons, and positrons, all drifting through an unimaginably vast and still expanding space. The temperature of this radiation will approach, but never quite reach, absolute zero. Every temperature difference will have equalized. Every gradient will have flattened. Every bit of energy will be so thinly dispersed across such enormous volumes of space that no work of any kind can be extracted from it. This is the heat death, maximum entropy, thermodynamic equilibrium on a cosmic scale. Nothing happens. Nothing can happen. Not because the laws of physics have changed, but because there is no energy gradient left to drive any process. No hot and cold, no concentrated and dispersed, no ordered and disordered. Just uniform, featureless, cold radiation stretching across a void that continues to expand forever. This is what the second law, followed to its conclusion, predicts. Not with certainty, because the second law is statistical, but with a probability so overwhelming that it might as well be certainty. The heat death is not guaranteed by a deterministic law. It is guaranteed by the same tyranny of large numbers that makes your coffee cool and your ice melt. The number of microstates corresponding to thermal equilibrium is so staggeringly, inconceivably larger than the number corresponding to any interesting structure that the universe will inevitably settle there. Not because it's forced, because there's nowhere else for it to go. Now, there is one last dimension to entropy that deepens the picture even further. It connects entropy not just to heat and energy and the arrow of time, but to information itself. In 1948, an American mathematician and electrical engineer named Claude Shannon was working on the theory of communication. He wanted to quantify how much information a message carries. How do you measure the difference between a meaningful signal and random noise? How do you calculate the capacity of a communication channel? Shannon developed a mathematical framework, and at its center was a formula that looked almost identical to Boltzmann's entropy equation. Shannon's information entropy measures the uncertainty or surprise associated with a message. If you know exactly what someone is going to say, the message carries no information. There's no surprise. But if the message could be any one of many equally likely possibilities, each one carries a lot of information, a lot of surprise. Shannon's formula counts the number of possible messages and takes the logarithm, just as Boltzmann's formula counts microstates and takes the logarithm. This isn't a coincidence. The two concepts are deeply related. Thermodynamic entropy is, in a precise sense, a measure of missing information. When you describe a gas by its temperature and pressure, you're specifying the macrostate, but you're leaving out an enormous amount of information about the individual positions and velocities of all the molecules. The entropy measures how much information you're missing. High entropy means you're missing a lot of information, because there are many possible microstates compatible with what you observe. Low entropy means you're missing relatively little, because there are few compatible microstates. This connection between entropy and information runs deep, far deeper than an analogy. It means that every physical process that increases entropy is also a process that reshapes what can be known about a system, and it connects to black holes in a disturbing way. When information falls into a black hole, it seems to be truly lost. The black hole has no hair, as physicists say, meaning it retains no external record of what fell in beyond mass, charge, and spin. But Hawking radiation appears to be thermal, random, carrying no information about what the black hole consumed. This creates the black hole information paradox, one of the deepest puzzles in theoretical physics. Does the information survive, encoded subtly in the Hawking radiation, or is it genuinely destroyed, violating the principle that information is never lost? Most physicists now believe information is preserved, that it leaks out in extraordinarily subtle correlations in the Hawking radiation over the black hole's lifetime. But proving this rigorously requires a complete theory of quantum gravity, which we don't yet possess. Even here, at the frontier of theoretical physics, entropy is at the center of the deepest questions. Let's sit with the information perspective a bit longer, because it illuminates entropy in a way that thermodynamics alone cannot. When Shannon developed his theory of information in 1948, he needed a name for his measure of uncertainty. The mathematician John von Neumann reportedly advised him to call it entropy, for two reasons. First, the mathematical formula was identical to Boltzmann's. Second, von Neumann said, nobody really understands entropy, so in a debate, you'll always have the advantage. The joke has a kernel of truth. The word entropy carries a mystique that sometimes obscures its meaning. But the mathematical identity between thermodynamic entropy and information entropy isn't a pun or a metaphor. It reflects a genuine physical connection. Consider a simple example. You have a single gas molecule in a box. The box is divided into two halves by a removable partition. You know the molecule is in the left half. That's one bit of information. You know where the molecule is. Now you remove the partition. The molecule is free to move through the entire box. You no longer know which half it's in. You've lost one bit of information, and the entropy of the system has increased by exactly the corresponding amount. This connection between information and thermodynamics was explored deeply by the physicist Leo Szilard in 1929 and later made rigorous by Rolf Landauer in the 1960s. Landauer showed that erasing information, destroying a bit, has a minimum thermodynamic cost. It generates a minimum amount of heat, increasing the entropy of the surroundings by at least Boltzmann's constant times the natural logarithm of 2 per bit erased. This is Landauer's principle, and it has been experimentally confirmed. Information is physical. Erasing it costs energy and produces entropy. This means that computation itself, the act of processing and erasing information, is subject to the second law. Every computer that runs, every brain that thinks, every process that manipulates information generates entropy as a fundamental byproduct. This casts the arrow of time in a new light. As the universe evolves from low entropy to high entropy, it isn't just dispersing energy, it's scrambling information. The exquisitely detailed information about the early universe, the precise positions and momenta of every particle, is still present in the current state of the universe. Nothing has been deleted. The laws of physics are deterministic at the fundamental level, meaning the current state contains, in principle, a complete record of the past. But that record has been so thoroughly shuffled, so completely smeared across such an enormous number of particles and interactions, that it is practically irrecoverable. The information hasn't vanished, it's been encrypted by entropy into a code of such staggering complexity that no conceivable process could decode it. Think about a drop of ink dissolving in water again, but this time from the information perspective. When the ink is concentrated in one small region, you can see where it is. That visual appearance encodes information about the arrangement of ink molecules. As the ink diffuses, that information doesn't disappear, it disperses. The ink molecules are still there. Their positions still encode information. But now that information is spread across the entire glass, mixed with the thermal motions of trillions of water molecules. To recover the original drop, you would need to know the exact position and velocity of every molecule in the glass, solve the equations of motion backward, and reconstruct the initial state. This is possible in principle. It's the time reversal symmetry of the fundamental laws. But in practice, it requires more information than any computer could store, and more computation than any machine could perform. The information is there, but it's been rendered inaccessible by the scale of the scrambling. This is what entropy does to information, universally and without exception. Every process that increases entropy takes information that was accessible and macroscopically visible and pushes it down into the microscopic details where it becomes effectively invisible. The past is written into the present at the molecular level, but written in a script so fine that no one can read it. The memories you carry in your brain are macroscopic, low-entropy records, physical patterns in neurons that encode your past experiences. They exist because energy was expended to create and maintain them, increasing entropy elsewhere. When you die and your brain decays, those patterns dissolve. The information about your memories disperses into the environment, joining the vast, scrambled archive of molecular motions that constitutes the universe's high-entropy present. The information persists, in principle. In practice, it is gone. This is perhaps the most poignant implication of entropy. The universe forgets. Not by destroying information, but by burying it so deep in microscopic complexity that it can never be retrieved. Every moment that passes, every process that unfolds, takes the detailed record of the past and shuffles it further into inaccessibility. Entropy is the universe's forgetting, and nothing escapes the forgetting because nothing escapes the statistics that drive it. So what does it truly mean to say nothing escapes entropy? It doesn't mean entropy is a villain. It doesn't mean the universe is doomed in some dramatic, tragic sense. It doesn't mean order is futile or that effort is pointless. What it means is that the statistical structure of physical reality is so overwhelmingly asymmetric, so spectacularly tilted towards states with more microscopic arrangements, that no process, no system, no structure anywhere in the universe is exempt from its constraints. Stars are not exempt. They burn their fuel and radiate their energy into the void. Black holes are not exempt. They evaporate over timescales that dwarf the current age of the universe, but they evaporate. Galaxies are not exempt. They will disperse their stars and merge with their neighbors and eventually dissolve. Life is not exempt. Living organisms maintain their internal order only by increasing entropy in their surroundings, and when the energy flow stops, the order collapses. Civilizations are not exempt. Every technology, every machine, every industry operates by degrading energy from useful to useless forms. Nothing that exists in this universe exists outside the reach of the second law. But notice what this really means. It means entropy is not a fate imposed on the universe from the outside. It's not a punishment or a curse. Entropy is the universe's own accounting system. It is the deepest bookkeeping that physical reality performs on itself. It arises from the simple fact that systems with many components have many possible arrangements, and some macroscopic conditions correspond to astronomically more arrangements than others. That's all. No mysticism, no cosmic design. Just counting. And the counting is so overwhelmingly one-sided that it governs the direction of virtually every natural process. There's something strangely comforting in this. The same entropy that will eventually lead to the heat death of the universe is the entropy that makes life possible right now. Without the low entropy starting point of the Big Bang, there would be no gradient to exploit. Without entropy increasing, there would be no arrow of time. Without an arrow of time, there would be no memory, no causation, no change, no experience. The same statistical tide that carries the universe toward its final equilibrium is the tide that allows stars to shine, planets to form, life to emerge, and minds to wonder about it all. Entropy isn't the enemy of complexity. It's the engine that drives it, at least for as long as there are gradients left to exploit. Right now, in this era, the universe is far from equilibrium. The sun still shines. Temperature differences still exist. Energy gradients are everywhere. And life, our kind of life, is riding those gradients with spectacular ingenuity, building complexity and structure and meaning from the slow statistical unwinding of a cosmos that started in an improbable state and has been exploring its possibilities ever since. That won't last forever, but it's lasting right now. And right now is all we've ever had. Entropy is real. It is physical, it is measurable. It is not disorder, it is not chaos, it is not a metaphor. It is the count of possibilities that the universe keeps, rigorously and without exception. And nothing escapes it, not because it's a prison, but because it's the fabric of probability itself, woven so tightly into the structure of reality that asking anything to escape entropy would be like asking something to escape mathematics. You feel entropy every time your coffee cools, every time you exhale, every time you watch a sunset, which is itself the product of nuclear reactions in a star, converting hydrogen into helium, increasing entropy, radiating photons across 93 million miles of space to scatter through an atmosphere and reach your eyes. You are entropy in action, a temporary, improbable, magnificent arrangement of matter and energy, maintaining your own internal order by exporting entropy into your surroundings. You will not last forever. Nothing does. But for as long as you're here, you are proof that entropy is not merely destruction. It is the condition under which all creation occurs. And that, when you finally see it clearly, is what entropy really is.